We'll start with rotational kinematics. Okay. Now, rotational kinematics, first thing that has to be very much clear in rotational kinematics, that it is not anything different from whatever kinematics we have done, apart from few extra terms that we need to learn. Okay. So first thing I will talk about is the delta theta. Delta theta talks about angular displacement. Okay. Angular displacement is basically how much angle traced by an object when it is moving on a certain path. So if it is going from here to here, what is the angle traced by it with respect to a center? That is the angular displacement. And it is always measured in radians. Correct? Now, one thing that we need to know exactly, one revolution is equivalent to 2 pi radians worth of angular displacement. Okay, so this is the thing that we need to know. So if I give you n number of revolution, so that will be n into 2 pi as will become your angular displacement. Okay, so always remember this. Also, you need to know the conversion between radians and degrees. Okay, so if there is a answer given in degrees, you can multiply by pi by 180 to convert your answer in radians. Okay. Okay. So one thing that we will do now is this is the first part, that is the second talk is the omega. This is not W, this is omega, this is angular velocity. And angular velocity is just angular displacement over time. But we need to know that it is also 2 pi by time period, or it is 2 pi into f. Okay, so what is the time period? Time taken to complete one rotation, and f is the number of rotations completed in 1 seconds. Okay, so this is the definition, and the units are radians per second. And the another thing that we need to know is alpha. Alpha is angular acceleration. Angular acceleration is rate of change of angular displacement. So final minus initial upon time, if you take, okay, that is the angular acceleration. Its radians, unit is radians per second square. Now, once we know those, so they are same as the kinematics that we learned in the first chapter, where there is a displacement, velocity, and acceleration. What is the continuation of that part? The continuation of that part is basically the same kind of SWOT equations that we have. Okay, so we can have SWOT of rotational kinematics. Now, this is something that is given in your data booklet, and the application is rather same as well. So, what are the four equations of SWOT we know? S is equal to ut plus half at square. So there will be, instead of S, there is a, so instead of S, there is a delta theta. Instead of U, there is a omega I, or you can write omega naught. Okay. Instead of V, there is a omega, and instead of acceleration, there is an angular acceleration, and time will be time only. So S is equal to ut plus half at square will be this instead of this. Now the another is S is equal to U plus V upon 2 into T. Another formula becomes V square is equal to U square. So final square is equal to initial square plus 2 alpha delta theta. And then you can have omega is equal to omega naught plus alpha t. So all those equations are very similar to what the SWOT of learned. And not only the SWOT equations are same, rather their application is also same. Like SWOT equation, there are 5 variables. They will always give you information about 3 only. Okay, so the other 2 you can figure out. Is that correct? And most of the time, instead of giving you delta theta, they will always give you number of revolutions. Just remember that. Okay, so number of revolutions given is the same of given delta theta. So by that sense, you can just convert using this relationship. But we have that exactly the knowledge about all the 5 variables. So if we have any 3 variables, you can figure out other 2. Also the graphs. The behavior of the graph is same. Okay, like for example, if I'm taking gradient in angular displacement versus time graph, that will be equivalent to the angular velocity, that is omega. If I'm taking gradient in omega versus t graph, it will give me angular acceleration, like how we do velocity versus time graph. It will give me angular acceleration. Another relationship is necessary, that is gradient is equal to gradient, not gradient, but rather if we take area under the curve, what we will get if we do area under the curve here, area under the curve in omega versus t graph. So that will give you the change in angular displacement. Okay, and the area under the curve in alpha versus t graph, that will give you change in angular velocity, that is final minus initial. Okay, is this clear so far? Anybody has any doubt in this? This is very straightforward. So what is the angular velocity of Earth? If somebody asks you, you can just do omega is equal to 2 pi by time period. Now, how much time Earth takes to complete one revolution is 24 hours. 24 hours, when you convert that in 26 seconds, 24 hours into 60 minutes into 60 seconds, that will give you the angular velocity of the Earth. Okay, so those kind of things you can probably calculate. Okay, second thing that we need to know is that these equations are only applicable if the alpha is constant. Okay, these you won't be able to apply this if alpha is not constant. Okay, so applicable only if alpha is constant. Okay, now just 1 second. Now once we know the basics of the rotational kinematics, there is a relationship that we should be aware of between rotational and translational kinematics. Okay, now in rotational and translational kinematics, what is the something that we should remember is that the length of an arc, which is also equivalent to the distance traveled. Let's say I am tracing an arc and the angle traced by me is given as delta theta. Now this is the arc length. Okay, and this is the angle traced between these points. So this will be equal to radius. If this is the radius times the angular displacement. So S will be equal to R delta theta. This has to be radius again. Okay, this is the formula that we should remember. The length of the arc of the distance traveled is radius times the angular displacement. The extension to this is V is equal to R omega. This is also an important formula. This is a linear speed and this is the angular speed. The same thing. Again, same relationship for acceleration also. Okay, this is linear acceleration and this is angular acceleration. Correct? So these are the relationship of that also you need to know, because sometimes you need the angular acceleration given and linear acceleration is needed. You can use those relationships. Okay. So once we know all those things, there is more important quantities that are on basis of which the questions are asked. The one is torque. Okay, what is a torque? The definition of a torque. A torque is given by this sign, that is tau, which is like a reversed mirror image of J. Okay, that's the symbol for torque. Now, torque is defined as it is a product of the force applied on the object and the perpendicular distance with respect to or between the force and the pivot of the object. Okay, so pivot is nothing but it is a fixed point. Okay, let's say if I am holding a pen, that the place where I'm holding, that is a pivot about which this object is free to move. Okay, so how do we calculate torque? With this. So imagine this is a object, and imagine this is a pivot about which the object is allowed to rotate. A pivot is the point about which the object is allowed to rotate. Okay. Now let's say the force is applied at this position, and this is the distance given. Let this distance be r. Okay. Now the torque won't be r times f because r is not a perpendicular distance. So what we do is, like, we extend the line of force. This is called a line of force. We extend the line of force and we take the distance perpendicular to the line of force. So this is the perpendicular distance that we are talking about. This perpendicular distance. It is not just any distance, it is a perpendicular distance. So this becomes, so if this is the angle theta that we know, where theta is angle between force and the distance r, then this becomes r sine theta. Correct? And in this case, the torque becomes force times r sine theta. Is this clear to everyone? Now, what is the other possibility? How we can calculate the same torque? See this. Same object, consider same object. Okay, consider another similar object. Again, this is a pivot. Again, this R is given. Again, this force is given. Okay, and this theta is also given. Okay. Now, in this case, what we can do is, the another way to do this is to take a perpendicular component of the force. So there are two possible components of this force. There is a F cos theta, which will be along the pivot. And there is a F sin theta. Okay. Now F sin theta becomes automatically perpendicular to the pivot. Correct. So the R automatically becomes perpendicular distance in this case. Perpendicular to F sin theta. Okay. So the torque in this situation is R into F sin theta. Now in both the methods, this is just a method 1. Okay, it is not the another technique, it is method 1 and this is method 2. In both the method, we are getting the same value for the torque, that is Fr sin theta. Okay, so it is up to you which method you prefer. Either you take a perpendicular component of a force or you take a perpendicular distance. Okay, now why doesn't there is a F cos theta is considered? Because F cos theta, the force, any force, it is not only F cos theta, any force acting through the pivot will never exert any torque. Okay, so whenever there is a pivot and if you apply a force that is passing through the pivot, okay, the line of the force is passing through the pivot, it will never cause any rotational motion. Is that clear? So this is the scenario for the torque. Okay, now once we understand the basics of torque, we need to revisit what is the definition of equilibrium. Correct? So I will talk about what we call this as rotational equilibrium. Okay, so in rotational equilibrium, sum of all torques or vector sum of all torque, that is equivalent of saying that torque is equal to 0. Okay, that is the equilibrium. Or we can see that sum of all, since there are only two possible directions of the torque, sum of all clockwise torque is equal to sum of all anti-clockwise torque. Okay, what is the unit of torque? The unit of torque is Newton meters. Okay, and this is the thing that you need to remember in rotational equilibrium. Okay. Now I will give you a simple question. Okay. Imagine, not that simple, but imagine a wall. Okay, this is a wall. This is a ground. Okay, and the and then there is a ladder. So this is a ladder. Now this ladder is stationary in the position shown in the figure. Okay. The information is that the weight of the ladder is 50 newtons. Okay, and the length of the ladder is 4 meters. Okay. If the coefficient of friction between wall and the ladder is equal to coefficient of friction between the ground and the ladder, and it is equal to 0.5 C. No, it is just 0.5, the coefficient of friction. Okay, then find the theta. Okay, are you able to understand this question? So how we will do this? So I understand that when the object is stationary, it is in two kinds of equilibrium. Okay, what are the two kinds of equilibrium we will have? The one equilibrium that the object has is the translational equilibrium. Okay, what do you mean by translational equilibrium? It means the net force is zero. Correct? Or you can say that all the forces are balanced. All the forces are balanced in a particular direction. Correct? Now first understand what are the forces acting on this object. Okay, there has to be a weight that is acting through center of gravity. Okay, so this is the center of mass or the center of gravity of an object that is basically at the middle of the object, and that is where the weight is acting, which is 50 newtons. Okay, now from the wall there will be a normal force, while there will be a frictional force from the wall. Okay, similarly there will be a normal force from the ground, and there will be a frictional force in the ground to the right. Now why it is to the right? Because if there was no friction force, this ladder will slide to the left, or it will move to the downward. So that's the reason why the direction of the friction is chosen in that case. Okay, so do you guys understand what are the forces acting on this object? Is this clear? Okay, now according to translational equilibrium, the net force is zero, so all the forces must be balanced. So all the vertical forces, what are the upward forces? The normal force from the ground and the friction force from the wall is balanced by the weight. So I can write normal force from the ground and friction force from the wall is equal to the weight, which is equal to 50 newtons. Okay, let this be equation 1. And the horizontal forces are normal force from the wall and normal force from the, frictional force from the ground are equal. Normal force from the wall is equal to frictional force, and that is our equation 2. Correct? Now, can we figure out anything else? So first thing that we figure out is that the friction force from the wall is coefficient of friction times the normal force from the wall. Correct? Which is basically 0.5 times NW. Okay. That is something that we do. But using equation 2, we can write the NW is equal to Fg, correct? Correct? From equation 2. And the friction force from the ground is equivalent of coefficient of friction times the normal force from the ground. So this will be 0.5 times 0.5 times Ng, which is basically 0.25 Ng. Okay. So what we got is this equation Fw. Okay, which we can probably substitute in equation 1. So using equation 1, we will get Ng plus, instead of writing Fw, I will write 0.25 Ng is equal to weight, which is 50. So we will get from this 1.25 Ng is equal to weight, that is 50. Okay, and if we divide Ng by 50 by 1.25, how much we will get? We will get approximately 40. Okay, so we got Ng. Now we can calculate the other values also. So Fg, that is the friction force on the ground, will be 0.5 times of Ng, that is just half of 40, that is 20 newtons. Okay, if we know what is Fg, Fw is just 0.5 times Fg, so that is half of this, so that is 10 newtons. Correct? And Nw was equal to Fg, so Fg was 20, so Nw is also 20. So now we have got all the values of the forces. Everyone understood this? How I got the values of all the forces acting on this? Now this is when I am just using translation equilibrium. The question is asking about theta. What is the angle? Now angle requires us to apply the rotational equilibrium. So what we will do, I will just copy this diagram. Let me just redraw it. Okay, we don't need to redraw, but I will just take the rotational equilibrium case now. Now when we do rotational equilibrium, so what will happen in rotational equilibrium? We have to take one of the point as pivot. So let's consider this point as pivot. Okay, even if that point is not fixed, we can consider any of the point as pivot. Okay, so we have to consider any point of contact as pivot. Okay, so if I fixed this point as pivot and the rod is like this. Okay, now what we need to understand here is the forces, like the weight is 50 newtons, but it is acting at certain angle. Okay, so if I take two components of this, it will be 50. So this is not, this can't be theta, this has to be theta. Because if you see the triangle, this is 90 degree, this can't be theta. So this has to be theta. Okay, so the perpendicular component of the force is 50 cos theta. Okay, and what are the other two forces? These are the other two forces. Now they are also working at an angle. So if this is theta, then this is also theta. So this component, a perpendicular component to the length of the rod, understand this is L by 2, and this is entirely the length of the rod, that is perpendicular distance. So this component becomes NW. So there is NW here, NW sine theta. Okay, while there is a friction here. So if this is theta, then this becomes theta. So for friction, there is FW cos theta. What I'm doing here is taking the perpendicular component of the forces with respect to the length of the rod. Correct? Because the torque is perpendicular component. So if I take clockwise torque, then the weight is exerting clockwise torque. The 50 cos theta is at a distance of 2 meters, which is, and this is 4, at a distance of the 2 meter is having a clockwise torque because it is making the rotate like this, and that is equal to Fw cos theta plus Nw sin theta into 4, that is giving all the anti-clockwise torque. Okay, as I mentioned earlier, sum of all clockwise torque has to be equal to anti-clockwise. This is 50 cos 2, it makes it 100 cos theta. Okay, and if we multiply Fw is how much? 10. So 10 into 4 is 40 cos theta, and Nw is 20. So 20 into 4 is 80 sin theta. Correct? Now, if we move the terms little bit, this will become 100 minus 40 cos theta is equal to 80 cos theta sin theta. So in that case, if we just write tan theta, it will be 60 over 80, or you can say 3 by 4. Okay. Is this clear? This is how we can get the theta value. Everybody understood this? Anybody has doubt in this? This is a lengthy problem, but we will get clear exactly what kind of a difficult problems you can get on torque related questions. Okay. Always one key point you need to understand: what is a pivot, what is the distance from the pivot, and are we taking the perpendicular component of the force? These three things you need to keep in mind. Okay. So that three things, if you keep in mind, then all the things are solved properly. Okay. Then ahead in this topic, what we have is a moment of inertia. Now, what is moment of inertia? Moment of inertia is a resistance to rotation, in simple words. Okay. So it is given by I. So higher the moment of inertia, less the object rotates. Okay, that's the simple thing that you need to understand. Okay. Now, what factors this moment of inertia depends on? Okay. So for point particles, if this is the axis of rotation, okay, about which the objects are going to rotate, and there are few point particles like m1, which is exactly distance r1 apart, or there is m2, which is exactly distance r2 apart. Okay, or there is m3, which is exactly r3 distance apart. So the moment of inertia is given by sum. This is a sum sign, sum of individual masses and individual distance square. Okay, that means it is equal to m1 r1 square plus m2 r2 square and so on. Okay, where r is the perpendicular distance from the axis of rotation to the mass. Is that clear? It is a perpendicular distance from axis of rotation to the mass. Okay, that's how we can. And we add the individual moment of inertia. Okay, so the sum of individual moment of inertia. Okay, that's what we are doing here. Now this is for point particles. Now for regularly sized object, what we need to consider for regularly sized object, the moment of inertia, for example, for a disk, the moment of inertia is just half mr square, where r is the radius, like this. Okay, or for the cylinder it is mr square. So this value for regularly shaped, okay, so this formula or expression, the expressions will be given in the question for the moment of inertia of regular objects. Okay, like for the sphere of radius r, if it is a sphere, it is equal to 2.5 mr square, like this. So it is different for every object. Okay, but we need to know that for regularly sized object like like there is a length of axis of rotation and there's a rod of length L, then the moment of inertia is like 1 by 12 ml square. So the formula has a fraction. That fraction is different for different object, and the expression will be given in most of the scenarios. So you probably don't need to remember. You just have to understand if there is a point size object, then the moment of inertia, how it calculates, that is something that you need to know. Okay. So for regular size object, you don't have to worry. The second thing about the moment of inertia that you need to know is that, so let's say let's say, this is an example. Let's say we have two objects, okay, on the same inclined plane. So we have two objects. This is both are the same cylinders, okay. Both have same radius. So we have one hollow cylinder and one has solid cylinder with same radius and same mass and released from same height. Which object reaches the bottom first? What do you think, guys? This is a hollow one and this is a solid one. Both have same mass, same radius, same inclined plane, everything same. Which will reach the bottom first? Yes, the solid reaches first. Why? Because the moment of inertia of the solid is lower than moment of inertia of the hollow one. Now, how do we know that? Because understand this, for the solid, all the mass is equally distributed about from the center, correct? But for the hollow one, the mass is concentrated away from the concentrated away from axis. Where is the axis of rotation? The center is the axis of rotation, correct? The mass is concentrated axis. Now, what is the distance? What are the factor it depends on? It depends on perpendicular distance from the axis. Okay, so higher the distance, perpendicular distance from the axis, the higher moment of inertia. Okay, so that's the reason why. So it has a higher moment of inertia, it will rotate slowly. Okay, and it will, since it has a less moment of inertia, it will rotate fast. Okay, so that's the reason why the solid will reach the bottom first. Is this clear, guys? Now, once we understand a concept of moment of inertia, let me give you what kind of a question is asked related to the motion of movement. So there is a question. Let's say there is a cylinder. Okay, this cylinder has moment of inertia 1 by 2 mr square. Okay, and there is a rope tied to the cylinder. We'll find this problem in the textbook as well as in question bank as well. And there is a mass of let's say m. Okay, now this has mass m. This also have mass m. Okay, now this object is tied with a string. Now this is a side view. Okay, from the front it will look like something like this. The object is circular and a string is attached, something like this. Okay, now this is at rest initially at time t equal to 0. Okay, let's say the block is released. Now the string attached to the cylinder allows the cylinder to rotate about the axis. Okay, to rotate as the block is accelerated downward. Correct? So the first thing that we need to ask, the question is, what is the acceleration? And second, what is the tension in the string? Okay. The third question, we can say that what is the angular acceleration? Okay. So in this question, what we need to do is we have to apply both the net force and net torque related formulas. Okay. So how do we do this kind of question? See this very quickly. For the mass, there is a tension acting upward and there is a mg acting downwards. And then there is an acceleration downwards. So if I write net force is equal to mass time acceleration for this object, mg minus tension has to be ma, correct? Now let this equation be like this only. Okay. Now for the cylinder, there is a torque. See, there is a weight of the cylinder. Yes, that is true. But the weight won't exert any torque because that is acting through the center. So any forces that are acting through the center won't exert any torque. The only torque that is exerted here is at the distance r away by tension. Okay, so r times tension. But here we will write one important formula that I haven't given you. The net torque has to be equal to I alpha. Okay, this is something that we will use here. So the net torque here, the only torque is this. So the net torque is this only. So this is equal to I alpha. Okay. Now, when we write RT is equal to I alpha, what is I? This is mr square alpha. And what we will get tension to be equal to, we can cancel out the r from here and we will get half m r alpha. Okay. Now, this is won't be enough. Now see this. We earlier we thought that linear acceleration is r times alpha. If we look at the beginning of this chapter, I will just remind you this. The linear acceleration is r times alpha, correct? So that is something that can use here to relate. So this t is actually half capital M A. This is equation 2. So if we substitute 2 in 1, what we will get? We'll get mg minus half Ma is equal to capital Ma. And if we solve this for A, what you will get, mg will be equal to 3 by 2 Ma. And by that case, we will get A to be equal to 2g by 3. Which is very nice. And the tension will be equal to half Ma. So half, the 2 will get cancelled. It will be just mg by 3 if we substitute this. And the angular acceleration is A by radius. So it would be 2g by 3r. Okay. Clear? Okay. So everybody understood this question, guys? Okay. So what we are doing here, we are using two formulas. Net torque is equal to mass time acceleration. Net torque is equal to moment of inertia times alpha, and net force is equal to mass time acceleration, and bringing them together by this relationship. These are the three important relationships for the torque related questions. Okay. What remains in this chapter is the energy and the momentum part, which is not that much, which is very much similar to what earlier we did. So let me just explain you this quickly. So like a translational kinetic energy, there is also rotational kinetic energy. Okay. And rotational kinetic energy is given as half I omega square. Okay. That is the angular speed and I is the, okay. So what is the application of this? See this. Imagine a sphere. Imagine a sphere of radius r is at rest at this position at height, let's say h. Okay, is at rest. When it comes to bottom, it will have both the speed. It will have linear speed and angular speed also, because it is rotating and it is moving, correct? So we can use this For example, according to conservation of energy, we can equate their energies. So initial energy will be equal to final energy. So initially it only has mgh. Okay, and at the bottom you can see that it has both the kinetic energy, translational kinetic energy. So translational kinetic energy is when object center of mass moves. Okay, this is when object moves, and the rotational energy is when the object rotates. So it is rotating as well. So m half mv square plus half I omega square. Okay, that will be the final energy. So starting with this equations, what you will get is mgh is fine, half mv square is also fine. Okay, we are supposed to find v in this case. So I is, let's say the I of the sphere is given as 2 by 5 mr square. Okay, the sphere is given 2 by 5 mr square. So 2 by 5 mr square I will do. And the omega, now remember this, v is equal to r omega I wrote initially. So omega has to be v by r. So omega square can be replaced by v square by r square. Okay, I can take this capital R. Now you can see that the r square get cancelled out, the 2 and 2 will get cancelled out. I will get half mv square is equal to half 1 by 5 mv square is equal to mgh. And we will get this as mgh is equal to 7 by 10 mv square. Solve the fraction, which will give us v to be equal to, you can cancel out the m on both the sides. We will get 10 by 7 gh plus square root as our velocity. Okay, this is clear, right? Rotational kinetic energy, very much similar to conservation of energy. It is just that if the object is rotating, we will add the additional kinetic energy. Okay. Now, the last part of this chapter is this angular momentum. Okay. We'll quickly do this. Okay, it is given by L. Now, what is angular momentum? Just try to remember that L is given as I omega. Okay, moment of inertia times the angular speed. But it is also equal to R times P. What is R? R is the perpendicular distance to the path of the object. Okay, just remember this. And M is the momentum of the object. Sorry, P is momentum of the object. Okay, this is for the singular object usually, but this is the angular momentum that we can calculate. Is this clear, guys? This is the angular momentum. What is the unit of angular momentum? It is so kg meter per second square is the unit for momentum. Kg meter per second. So this is meter square second raised to minus 1. That is the unit, you can say. Now, what is the unique about angular momentum? For example, if this is the axis of rotation, okay, this is the axis of rotation, and the object is going in this direction, it has a velocity. Okay, let's say I don't know the moment of inertia, but I know the perpendicular distance to the object. The perpendicular distance is r, and the mass of the object is m. Okay, if this is the axis of rotation, and if this is the perpendicular distance, okay, with respect to the axis, then we can write L to be equal to mvr. Okay, now can we use the I omega square also? See, moment of inertia, if I calculate, moment of inertia is mr square, and it is omega. Okay, omega can be written as v by r. So this will give me same mvr as an equation. Okay, all those equations, all those calculations are same in that sense. Clear? So you can either use any of this, but one thing that you need to remember, we are interested in calculating angular impulse, and angular impulse is basically final minus initial you need to do here. So final, what? Yes, yes. Correct. See, positive. It depends whether what you are considering. So if you are considering initial to be clockwise and you are considering clockwise as positive, then you can see that final is anti-clockwise, so it will be opposite. Yes, so it will two will add up. It won't be zero, obviously. Okay, there will be a torque. Okay, so whether it is positive or negative, it depends on what you are considering positive. Whether you are considering clockwise as positive or anti-clockwise as positive, but it will still add up. The magnitude will remain twice of the initial. Okay. Uh, Now, why we calculate angular impulse? Because the torque, which already has multiple formulas like RF sine theta, it also has formulas of I alpha. There is one important formula that it is change in angular momentum over time. Okay, this is the formula for the torque. Now, what is the implication of this formula? There are graphical implications. First of all, if there is a torque versus time graph, the area under the curve is change in angular momentum. This is something, there is a question on this. So remember, there is a torque versus time graph. Area is change in angular momentum. And if it is angular momentum versus time graph, then the gradient is equal to the net torque. Okay, these are the implication of these two formulas. And one final thing, okay, is that if the torque applied, if there is no external torque, if there is no external torque acting on the system of objects, then the total angular momentum, not the angular momentum of the single object, but the total angular momentum of the system remains constant. Okay. So if there is no angular, there has to be total angular momentum has to be constant. Okay. And there is a classic example for this. Imagine there is a person holding a wheel. Okay. And this wheel is rotating in anti-clockwise direction. Okay. And there is a person that is holding an axis. Person is holding the axis to this wheel and he is sitting on a rotating chair. Okay. So this is a rotating chair. And this person is holding this wheel. Okay, this wheel is going anti-clockwise. Now, in this case, the initial angular momentum is the angular momentum of the wheel only. Correct? Now, if the person twists the wheel, okay, if the person twists the wheel, what will happen to the person holding the wheel? And the turntable? See this. What the person is doing now? He is changing the direction of the wheel clockwise. Okay, so he have twisted his hand, and he is making the wheel to go clockwise now. So he has basically rotated like this. He has exchanged his arms. Okay. Now what will happen? The final angular momentum will be negative of the wheel, because wheel is going in opposite direction now. Correct. So you can see that if you just consider for the wheel, the angular momentum is changed. Correct. But what happens is, like, since this is at rest. Okay. This chair is at rest because there is a conservation of angular momentum. This has to be conserved and there is no external forces. What happens is, like, this person starts rotating in anti-clockwise direction. Okay, the chair rotates in anti-clockwise direction. Why? Because it has to balance the angular momentum both initially for the wheel, okay, and for the chair also. Okay, and the angular momentum of the chair in that case will be twice of that of wheel. So this is all it is there in rotational dynamics.